There's there's an interesting question in Dory that Tom, I'm not sure if you will be able to answer, but I feel like it's a good starting question. This may possibly be a bit off topic, but if I spray my dog with spot remover, what will happen?
Oh man, I think that's my dad has joined. Yeah, but I think your dog would disappear. It sounds pretty cut and dried to me. He threatened to ask that sort of question, so that's fine.
Yes. Okay. Yeah. Let's get started. So, hello everybody, and welcome to another NLP with Friends. We're really happy to see everyone, and we're really stoked to have Tom McCoy with us today, who is an awesome PhD student from the Cog-Sci department at Hopkins. We're going to turn it over to him in just a second, but reminders before we get started. We're going to use Dory to collect questions, as well as the raise hand function in Zoom. If you have a question during the talk that you think should be answered pressingly for your understanding going forward, you can click raise hand in the participants panel. And otherwise, we'll ask questions at the end and hopefully have a nice discussion. When using Dory, if you want us to be able to call on you so that you can ask your question, please give a name, because otherwise we will say things like, "Dear Champagne Octopus, you had a question." These are the sort of anonymous names from Dory. So thank you all for coming. And without further ado, I'm going to turn it over to Tom.
Thank you. Let me share my slides here. Yeah, so morning, everyone. I'm really excited to be here. Thanks to Abhilasha, Liz, Yanai, and Xerox for creating the series. I think it's really a great idea. And especially thanks to Liz for inviting me on. So the work I'll be discussing today is about universal linguistic inductive biases via meta-learning, which is a collaboration with Aaron Grant, Paul Swansky, Tom Griffiths, and Tollinson. Learning a language, whether it's being done by a human or a computer, depends on two types of factors. First, it clearly depends on data in the language, but there's no such thing as learning from data alone. Learning also always depends on properties of the learner called inductive biases, which are the factors that affect how the learner will generalize beyond the data. Here's an example of inductive biases at play. We have two learners here who have been told that the blue square is an example of a DAX and the green triangle is an example of a BLIC. And now they must answer whether the blue triangle is a DAX or a BLIC. Well, the learner on the left has an inductive bias for generalizations based on shape. So this learner would reason that DAX means square and BLIC means triangle, and therefore the blue triangle is a BLIC. While the learner on the right has an inductive bias for generalizations based on color. So this learner would reason that DAX means blue object and BLIC means green object, and therefore the blue triangle is a DAX. Crucially, even though both learners saw the exact same data, they've made different generalizations because they have different inductive biases. Why are inductive biases important for NLP? Well, current state-of-the-art models are without a doubt impressive, but they still have some major weaknesses. And two of their most important weaknesses are directly tied to the notion of inductive bias. First, these models generally require massive training sets to learn anything useful, and they also usually generalize poorly to novel types of examples that differ in some meaningful way from the examples they were trained on. Both of these shortcomings could be fixed via inductive biases, because inductive biases help guide the course of learning, so they can help to make learning faster and more efficient, and they can also improve how the model generalizes once learning has concluded. The question then is, how can we give the needed biases to our models? In this work, we introduce a framework for doing that, a framework for giving linguistic inductive biases to a neural network model. Our framework has 4 steps. First, we define the inductive biases that we wish to impart. Then we translate those biases into a space of languages which encode the biases. Next, we have a model meta-learn from languages drawn from that space of languages. I'll define meta-learning in more detail soon, but briefly, the way this works is that we expose our model to a large number of languages drawn from our space of languages. And over the course of this process, our model gains the ability to learn any language in the space of languages from a small number of examples. Our hope is that by giving our model the ability to learn these languages quickly, we will also give our model the inductive biases that were used to define the space of languages. To see whether that hope was borne out, we move to the final step of our pipeline, which is to analyze our model to see if it has indeed meta-learned the intended biases. This framework is very general and could in theory be applied to any aspect of language, from phonetics to semantics. In this work, we're going to focus on one particular case study from phonology, namely syllable structure. And to preview our results, we find that meta-learning successfully imparts all of the target inductive biases that we sought to impart. So that was a high-level overview of the work. And now just to go over how the rest of the talk is going to go, I'm first going to go over our motivation in a little bit more detail to hopefully drive home why I think these problems are important. And then I'll walk through the 4 steps of our framework as they apply to our case study of syllable structure. Then in the spirit of this speaker series, I'm going to talk a little bit about the course of the project, what worked and what didn't, and surprises that came up along the way, as well as some discussion points of things that I would love to talk about, to hear your thoughts on, get any feedback. And then that should leave about 25 minutes at the end for Q&A about these discussion points or anything else you're curious about. So first, to go over our motivation in more detail. As I mentioned, inductive biases are important because they might help us overcome 2 major weaknesses of current models, namely their reliance on massive training sets and their poor generalization to novel types of examples. So now I just want to give a more concrete example for each of these 2 points. First, regarding the fact that current models require massive training sets, this graph compares the number of tokens that a human child has seen by age 10, which is an age when you can reasonably say the child has acquired their language, compared to the number of tokens that GPT-3 was pre-trained on. And it's a little hard actually to estimate exactly what the number should be for the humans here. Depending on which culture a child is raised in, it might range anywhere from 10 million to 100 million. But honestly, it doesn't really matter exactly how you estimate the number for humans, because no matter how you do it, the bar for the humans is going to be so much smaller than the bar for GPT-3 that you won't even be able to see it. So humans give us an existence proof that it's possible for a learner to acquire a language from far fewer examples than our models are currently using. And it would be nice if we could transfer some of this data efficiency to our models as well. Then the second weakness I brought up was that current models generalize poorly to novel types of examples. To illustrate this, I'm going to use the task of natural language inference, which is a task where you give a model 2 sentences, such as the doctor by the lawyer saw the artist, and the model must then determine, and the second sentence is the doctor saw the artist, and the model must then determine whether the first sentence entails that the second sentence is true. In this case, the label would be entailment, because the doctor by the lawyer saw the artist entails that the doctor saw the artist. And if you take a standard model such as BERT and train it on the popular data sets for this task, such as the MNI data set, BERT will perform very well. As you see in this plot, BERT gets around 84% accuracy on the MNI data set, which is very impressive. But several authors have noted that this MNI data set supports a heuristic of assuming that the label will be entailment anytime there's a high amount of word overlap between the 2 sentences. In the example I have shown here, this heuristic works because there's a lot of word overlap between the 2 sentences. Every word that appears in the second sentence also appears in the first sentence, and the label is indeed entailment. But even though this heuristic generally will yield the correct answer in this particular data set, we can easily imagine examples where the heuristic fails. For instance, the artist saw the doctor does not entail the doctor saw the artist, even though we have complete word overlap between the 2 sentences. So in some past work with Ellie Pavlik and Tal Linzen, we created a data set called the Hans data set, which contains some examples where the heuristic works and some examples where the heuristic fails. And when we evaluate BERT on these examples in the Hans data set, we find that BERT does very well on the examples where the heuristic works, but it does very poorly on the examples where the heuristic fails. So these results give one clear example of a case where a model does very well on examples that are similar to the ones it was trained on. In this case, examples where the heuristic works, but then it generalizes very poorly to examples that differ in some meaningful way. In this case, examples where the heuristic fails. And there are many, many other works in the area of analysis of neural networks with similar findings of how these models tend to generalize poorly to novel types of examples. If we want to fix these shortcomings, we need to give our models better inductive biases. There are really 2 problems that need to be solved in order to make this happen. first we need to figure out which inductive biases are needed, and then we also need to figure out, given those inductive biases, how can we give them to our models? And I want to stress that problem number 2 is far from trivial here. For example, people have been saying for a long time that our models need an inductive bias for compositionality, and yet the field has still not settled on a good way to actually give that sort of inductive bias to our models. In this work, we focus on problem number 2, where we will be proposing a technique for giving particular inductive biases to a neural network. So we don't really get at problem number 1 of which specific inductive biases will actually be most useful for our models, although I will note in passing that our framework could be used to study that question, because now that we have a way to give inductive biases to models, we can use this method to create a bunch of different models that all have different inductive biases, and then see which of those models perform best to gain some insight into which inductive biases are most useful. So once again, here's the outline of how our framework works. And the first step is to define the inductive biases that you wish to impart. So to do this, we need to decide on which phenomenon we want to have our model learn. And in choosing a phenomenon, we wanted to pick something that was simple enough for us to understand it well, but complex enough to be interesting. For this purpose, we chose a phenomenon from phonology, namely syllable structure typology. And in particular, we're adopting the account of syllable structure from a linguistic formalism known as optimality theory. I want to stress that our framework does not depend on optimality theory in any way. This is just the particular use case that we chose to illustrate the framework. In optimality theory, we assume that every word has some underlying form, which is a sequence of sounds, such as KTA, and a surface form, which is a sequence of syllables, such as ka-ta. Languages differ in how the underlying form is transformed to the surface form. For instance, one language might turn KTA into ka-ta by inserting an A, while another language might turn it into ka by deleting the T. And this mapping between the input and output is governed using 4 constraints, which I will illustrate here using 3 possible input-output pairs, where the input is always BIP, but the output could be bib, bippa, or bip. The first constraint is called onset, which says that every syllable should start with a consonant. All 3 of our examples satisfy this constraint. And by the way, the constraint is called this because a syllable's onset is a consonant at the start of the syllable. The second constraint, no coda, says that no syllable should end with a consonant. It's called this because a coda is a consonant at the end of a syllable. In this case, our third example violates the constraint because its syllable ends with a consonant P. Next, no insertion says that nothing should be inserted into the input, which is violated by the second example because an A has been inserted. And no deletion says that nothing should be deleted from the input, which is violated by the first example because the P has been deleted. These constraints are not arbitrary. They are motivated by universal statistical tendencies of the world's languages. For instance, across languages, we have observed a preference for syllables that begin with consonants but do not end with consonants, which motivates the onset and no coda constraints. Sometimes these constraints can conflict with each other. For instance, the no coda constraint would push a language to choose one of the first 2 mappings rather than the third one, because the third one violates the constraint. However, if you wanted to choose one of the first 2 mappings, you would have to violate either no insertion or no deletion. So in this case, no coda conflicts with no insertion and no deletion. When such conflicts arise, they are resolved with a ranking of the constraints. For instance, if we rank the constraints in the order shown here, with onset ranked highest, then no coda, then no insertion, then no deletion, with that ranking, the first mapping would be the one that wins because it's the one with the least serious constraint violation. That is, the only constraint it violates is the lowest ranked constraint. However, if we reorder the constraints using some very sophisticated animation, now the third mapping will be the one that wins because now it's the one with the least serious constraint violation. So this example illustrates how differences in the constraint ranking explain why languages differ in the mappings that they allow. So this optimality theory framing is the set of inductive biases that we want to give to our model will be some set of biases that encode knowledge of this optimality theory frame. And in order to give our model those inductive biases, we now need to translate those biases into a space of languages. We will define a single particular language as follows. First, we need to choose which consonants can appear in the language and also which vowels can appear in the language. Next, recall that sometimes when you're mapping the input to the output, you need to insert sounds. So for this language, we also need to choose which consonant will be inserted when we need to insert a consonant, and which vowel will need to be inserted when we need to insert a vowel. And finally, we need to choose a ranking for our 4 constraints. So the set of constraints that we use is always the same across languages, but the ranking needs to be chosen separately for each language. This is how we define one single language, and now our space of languages is simply the set of all languages that could be generated in this way. Now that we have our space of languages, we're going to have a model meta-learn from languages drawn from that space. This is really the most important step of our pipeline. The model we're going to be using is a sequence-to-sequence neural network, specifically an LSTM without attention, just a plain vanilla LSTM, which reads in the input one symbol at a time, and then generates the output one symbol at a time, where the input is a word's underlying form, such as BIP, and the output is the word's surface form, such as BIF. Before I define how exactly meta-learning works, I'm going to review how standard learning in a neural network works so that I can contrast meta-learning with it. So our model, just like any neural network, is governed by a large number of numerical parameters, which we can visualize as this parameter space. Hopefully, there will be some range of values for these parameters, which will enable our model to perform well on the input-output mappings for a particular language. We can visualize that range of parameter values as a region in the parameter space. The problem is that we don't know where this region is. So the usual practice is to initialize the model's parameters at some randomly selected point, and then to train the model on a large number of input-output pairs from the language, where after each input-output example, the model's parameters are adjusted slightly, such that if the model saw that same example again, it would perform a little bit closer to the correct answer on that example. And after many such adjustments, the model's parameters will end up at a place where it can now perform input-output mappings with high accuracy for this language. So in standard learning, the goal was to have the model learn one particular language. Now in meta-learning, the goal will instead be to give our model the ability to learn any language in our space of languages. For this reason, it's sometimes known as learning to learn. The variant of meta-learning that we use is MAML from Finn et al., which learns a parameter initialization that supports rapid learning. Here's how MAML works. Just like before, we'll be working in the model's parameter space, but now instead of having a single language, we have an entire space of possible languages. And just like before, we will initialize our model's parameters at some randomly selected point. And now we will sample one language from our space of languages and train the model on examples from that language using a small number of steps of standard learning. At the end of this small number of steps, we will figure out how we could adjust the model's initialization such that if we trained the model again from the new initialization, it would perform a little bit better on language 1 than it did with our original initialization. So this adjustment is computed using some second order gradients. And then we adjust the model's initialization accordingly. Then we sample another language from the space of languages, train our model on a few examples from that language, and adjust the model's initialization such that if it were trained on language 2 again, now it would perform a little bit better on language 2 at the end of training on that language. We keep repeating this with more languages sampled from our space of languages until eventually, hopefully, the model's parameter initialization will end up at a point from which it could readily learn any language in our space of languages. An important aspect of MAML is that it mainly encodes the model's inductive biases in the model's parameter initialization, whereas other approaches for giving inductive biases to a model often will instead focus on the structure of the model's architecture. In our experiments, we're going to compare a model initialized with MAML to a randomly initialized model. It's important to note that these two models are identical in their architectural structure. They differ only in their parameter initialization. So now that we have our model, which has meta-learned on a bunch of languages from our space of languages, we now hopefully have successfully given our model the inductive biases that we use to define that space of languages. But now the last step of our framework is to analyze the model to see if that actually did happen. To first give an initial look at how exactly our model is performing after meta-learning, I'm going to show some screenshots from our project website. So this is what the demo looks like, and I'm going to walk through the different components of the demo step by step. So first, our goal is to train our models on performing input-output mappings for one particular language. In the language that we've chosen, the syllables of the output must always be of the form consonant-vowel. And in order to satisfy that restriction, sometimes we don't need to do anything because sometimes the input is already of the form consonant-vowel, but other times we need to insert a consonant, specifically the consonant D, or a vowel, specifically the vowel E, or sometimes you need to insert a mix of both. And in these columns, you can see the predicted outputs from our two models, one model that was initialized using MAML and another model that was initialized randomly. So even before we have trained on any examples in this language, you can see that the model initialized with meta-learning is getting this example right. And this is actually not too surprising, because in the optimality theory framework that we've adopted, no matter what language you're working in, an input of the form consonant-vowel will always map to itself as its output. So it's encouraging to see that our model has meta-learned that universal fact about languages. However, the rest of the inputs in this test set cannot be handled by such universal reasoning. So to teach our model the rest of these examples, we need to train it on some examples from the language. So first, we've trained our models on one example from this language, and you can see that the model's predicted outputs have changed, but they're still getting most of them wrong. So now we've trained on 2 examples, 3, 4, 5, 6, 7. Now after 7 examples, you can see that the model initialized with meta-learning is getting several more examples right, but it's still not all the way there. Now we've trained on 8 examples, 9, 10, 11. Now, after training on only 11 examples, the model initialized with meta-learning is scoring perfectly on its test set, while the model that was randomly initialized is still just generating nonsense. So in this case, our model initialized with meta-learning only required 11 examples to learn this language perfectly, whereas the randomly initialized model usually requires somewhere in the order of a few thousand examples. This rapid learning that we saw in the demo gives some indirect evidence that our model has the inductive biases that we want it to have. However, for a more direct evaluation, we want to perform some targeted tests because in the paper, we defined in more detail 6 particular inductive biases that we wanted to give our model, and we want to be able to tell whether our model actually has those 6 particular biases rather than some just generally improved learning capability. So in order to take this targeted look at which inductive biases our model has, this does raise the question of how can you tell what inductive biases a model has? And this question is, in fact, a bit tricky. So for example, one thing that does not work is to simply look at the model. Because if you just look at how our model is structured, it looks like a standard garden variety LSTM. The only thing that makes it special is its parameter initialization. You might be able to gain some insight by analyzing the topology of the initial weights, but number one, I think that would be very tricky to do. And number two, given how poorly we understand these models, I don't think we could be especially confident in insights we would gain from that sort of analysis alone. So the one type of approach that I think robustly does give us insight into a model's inductive biases is to analyze the model's learning behavior. The reason why this makes sense is that inductive biases are influences on how a model learns. So if you want to see what inductive biases a model has, you need to analyze how it learns. And we're going to look at 2 different approaches for analyzing the model's learning behavior. The first approach is to look at ease of learning. The intuition here is that if our model finds it much easier to learn languages of one type than languages of another type, that gives us evidence that our model has a set of inductive biases that favor the easier to learn languages over the harder to learn languages. Second, we'll also look at generalization, where we train our model on a training set that withholds certain types of examples and then see how the model generalizes to that withheld category of examples. So the idea here is that looking at a model's generalization of any sort always does depend on the inductive biases. But in this particular type of case, the inductive biases stand in especially stark focus because we've constrained the training set such that the training data gives little indication of how those types of examples should be handled, leaving the model's choice of how to handle those examples extremely dependent on the model's inductive biases. In linguistics, the sort of setup where certain types of examples are missing from the training set is known as a poverty of the stimulus scenario. So in our paper, we look at 3 different examples for each of these 2 approaches. In the talk, I'm only going to go over one example of each, but if you're interested, I'd be happy to go over the remaining 4 examples during the Q&A period. First, as an example of the ease of learning approach for analysis, we're going to look at inductive biases relating to the set of constraints that define our languages. Recall that in the framing we've adopted, we use the constraints onset and no coda, which say that every syllable should begin with a consonant but should not end with a consonant. However, you can easily imagine two alternate constraints called no onset and coda, which instead say that every syllable should not start with a consonant but should end with a consonant. So here we want to figure out whether our model has a bias for the correct set of constraints, onset and no coda, over the incorrect set of constraints, no onset and coda. And to test this, we will test whether it is easier for our model to learn languages defined with onset and no coda than languages defined with no onset and coda, where we quantify ease of learning by the number of examples that are required for the model to reach 95% accuracy on the validation set. So here are the results. Each bar in this plot is an average over 100 languages. And looking at the two edges, you can see that our model requires far fewer examples to learn a language defined with the two correct constraints than a language defined with the two incorrect constraints. And for languages defined with one correct constraint and one incorrect constraint, the model requires an intermediate number of examples. So these results indicate that our model has meta-learned an inductive bias favoring the correct constraints over the incorrect constraints. As an example of our second analysis approach through generalization, I'm going to look at something called implicational universals. Under the optimality theory account that we've adopted, the presence of certain mappings in a language implies the presence of certain other mappings. For instance, if a language maps an input of the form vowel consonant to an output of just a vowel, it's also guaranteed to map an input of the form consonant vowel consonant to an output of consonant vowel. Now, this certainly does not have to be the case. You could create a framework where this implication does not hold, but in the framework we've adopted, this implication does hold, so we want our model to be aware of the implication. Such implications are called implicational universals. To test whether our model has a bias for the particular implications that hold in our framework, we're going to train our model only on inputs of one type, such as inputs of the form vowel consonant, and then test how it generalizes to inputs of a different withheld type, in particular a withheld type that forms the other half of some implicational universal, in this case, inputs of the form consonant vowel consonant, to see whether our model is able to leverage the implicational universal to generalize from the type of example it's seen to the withheld type. So here are the results. You can see that both of our models perform well on the type of example that they were trained on, the pink bar here. But only the model that was initialized with meta-learning is also able to generalize well to the novel example type, which shows that meta-learning has given our model an inductive bias for these particular implicational universals. So in the paper, we also look at some more examples with these two analysis techniques. So with the ease of learning technique, in addition to looking at the example I showed you of the correct set of constraints, we also see whether our model has meta-learned a bias for consistency of the constraint ranking used within a language. That is, does our model know that within a given language, you have to use the same constraint ranking for all types of inputs? And also we look at the consistency of the set of constraints. That is, has our model meta-learned that within a given language, you have to use the same set of constraints for all of the inputs? And then with the generalization method, in addition to the implicational universals example that I showed you, we also look at how our model generalizes to inputs of greater lengths than it saw during training, and how it generalizes to inputs containing novel symbols, that is, containing some letter that never appeared in its training set. So if you're curious about any of these, feel free to ask about them in the Q&A period. So to conclude, meta-learning with MAML successfully imparted all of the inductive biases that we specified, which shows that meta-learning with MAML can improve both the data efficiency of our model, since we saw that the meta-initialized model learned much faster than the randomly initialized model, and can also improve its generalization to novel types of examples. One of the points of this speaker series was also to talk about not just the endpoint of the research, but also to talk about the process, what worked, what didn't, and any surprises that came up along the way. So in fact, I think that the overall trajectory of this project, in terms of how I viewed it, really was quite a sequence of surprises for me. So when I was starting this project, I was coming off of the first project for my PhD, which was this work with Bob Frank and Tom Linson called Does Syntax Need to Grow on Trees?, where we were trying to figure out which types of approaches are successful for giving a particular inductive bias, namely a hierarchical inductive bias, to a neural network model. And our basic conclusion from this work was that the only thing that robustly works is choosing some model architecture that is motivated by the inductive bias you want. We tried a bunch of other things and none of them reliably worked. And after finishing this work, I started to hear about MAML. And because we'd had so little success with everything besides model architecture in our past work, I just assumed that MAML had no hope of working. But I thought, okay, I guess I'd better try out MAML just so that I can definitively show that it's useless and that it has no hope of giving specific inductive biases to a model. So I started to play around with MAML, and it actually seemed to be working pretty well on the examples I was throwing at it. So I figured, okay, I must just be using examples that are a little bit too easy. Let me throw something harder at the model. But then MAML still kept working really, really well. So even though I came into this project being really skeptical about MAML, I ended up being very enthusiastic about it. So I think there were a couple important takeaways from this for me. So first, it shows how it's really important to not get too attached to any one particular approach or formalism, because if you do that, you might miss other approaches that are equally promising. And I think more generally, this also shows that even if an experiment does not turn out the way that you expect it will turn out or the way that you want it to turn out, it might not be such a negative thing. So here I was sort of expecting / hoping for MAML to fail, but it ended up working really well. And now I'm really happy with the project we ended up based on MAML's success. So another sort of situation where this might arise is if you find that your model or some new approach you're proposing fails to outperform some simple baseline. Well, of course, that's really discouraging when it happens, but the fact that the simple baseline does so well might actually be an important finding of its own right. For example, maybe the reason that the simple baseline worked so well is that the data set you're using is too easy. And if that's the case, that's a really important finding for the field, because we really rely on having high quality data sets to assess progress in the field. And if our data sets are too easy, that can skew our perception of which models work and which don't. So if you can show definitively that some popular data set is too simple or too easy, and especially if you can then propose a better data set, that can really be an important and impactful finding, which might in fact be more impactful than the point you originally set out to demonstrate. Another big challenge in the course of this project was simply implementing MAML in PyTorch. So there already existed some good implementations of MAML in TensorFlow, but I wanted to stick with PyTorch because that's what I'm familiar with. But it turned out that PyTorch really was not set up to make MAML easy. So after a lot of head banging and consultation with Aaron Grant, my co-author, we eventually did get it working. And then kind of ironically, as soon as we finally got this working, this group of authors came out with a very nice framework called Hire for implementing meta learning in PyTorch. So certainly we could have been saved a lot of work if we had just waited a couple months for this to come out, but I still think it was a useful experience to learn how to implement MAML in PyTorch on our own, because I definitely had to gain a better understanding of gradient descent to do that, and that really helped me think through this project. And the last thing that was challenging, but also very rewarding, was just working with a large group of collaborators who have very different backgrounds and different interests. So this is at times challenging because when everyone's coming to the table with different perspectives, that can make it really hard to create a final paper that everyone's happy with and that everyone thinks addresses all the important points. And it can also be very hard simply to find a meeting time that works for everyone. But overall, this definitely strengthened our final product, and I think increased the appeal for audiences coming from different backgrounds. So I think it's also important to keep in mind when you're collaborating with a large group that it will at times be challenging, but that the challenge can really be worth it. Okay, yeah, so we should have a fair amount of time for discussion, and I put here some of the discussion points that I'm especially interested in. So I'll go over this list briefly, and you're welcome to ask me about any of these points or anything else you find interesting. So the first point that I think is really important is scaling this approach up. The example I've shown you here is only with a very small, carefully constructed data set, which I think is very important as an initial step for establishing the viability of your approach. But of course, we don't want to stop there. We want to see if this can actually work for more naturalistic data or more realistic data sets. So I think there are certainly some additional challenges that remain for doing that. And one particular open question that's very important is, given that our approach relies on meta-learning from constructed data, will the inductive biases that are imparted in this way be able to generalize to naturalistic data? So I think that question is very important, and we simply haven't tested it at all yet. Another couple discussion points that I think are important are comparing our framework to other potential approaches for giving inductive biases to a model. So one aspect of this is whether you should do meta-learning from constructed languages, as we did in our approach, versus meta-learning from natural languages using existing corpora, which is an approach that most of the other papers in NLP that have used meta-learning have adopted. So there are certainly advantages and disadvantages of both approaches, and I'm happy to talk about those advantages and disadvantages. And more generally, I think it's important to compare using MAML to impart inductive biases to other approaches. In particular, as I hinted at earlier, I think the main other alternative approach is to design the model architecture in a way that is meant to impart the inductive biases. So I think there are some situations where that approach would be easier and other approaches where MAML would be easier, and potentially some fruitful ways of combining the two approaches. Another important question to ask is, what are the limits of our approach? Which inductive biases could be imparted using this approach, and which ones would be harder to impart? And then finally, I'm happy to, I do have some bonus slides for the analyses that I did not include in the talk, but that are in the paper. In particular, using the ease of learning approach to look at some more abstract biases governing the consistency of the constraint ranking and the consistency of the constraint set, and also using the generalization approach to look at how our models generalize to greater length and to novel symbols. So thank you, and now we have time